Good morning, ladies and gents. Welcome to the last lecture of the week. Just as a reminder, I already said this from the previous lecture, but we did finish the alkynes lecture early. We did it all in one day yesterday. So that gives us an opportunity to do the radical reactions lecture today on Thursday, so that next week you have a day off before the final exam. We'll do synthesis on Monday, we'll do alcohols on Tuesday, and then you'll have Wednesday with no lecture, no new materials at all. There might be a couple things due, but I don't know. I can't remember exactly what it is. But you won't have any new material on Wednesday, so you can take a break from learning and study and practice for the final exam. So today's lecture on radicals, again, it's going to be kind of a long one because we're kind of squishing it all into one day here. But just know, again, it's not as long. It's not any longer than any other lecture. But just remember, though, this exam 4, that is tomorrow, will contain information on addition reactions of alkenes, okay, alkynes, and also radical reactions. Okay, so all that stuff needs to be taken into account for your 4th exam on Thursday. All right, so let's go ahead and get started. I'll change the view here. There we go. Radical reactions, lecture 15. Wow, I can't believe it. We're already on lecture 15. The class is almost over. All right. Had to hydrate myself before we get into radicals. Okay. So let's do a little quick introduction on radicals. Free radicals form when bonds break homolytically, which we talked about that before. And so here we have a homolytic bond cleavage, and that's signified by a single barbed arrow or fishhook arrow, right, going in opposite directions. And what that means then is that X will get one single electron, and then Y will get one single electron, and those are both called radicals. Okay. Note that a single barbed or fishhook arrow is used to show the electron movement, right, as opposed to this, which is a double barbed arrow, right. That's for a pair of electrons moving. We were definitely working with the single electron moving today with the fishhook. Okay. Recall that the orbital hybridization of carbocations and carbanions, right? sp3 hybridized is trigonal pyramidal, right? And then sp2 hybridized is trigonal planar, okay? And then the filled orbital here is this sp3 orbital in the carbanion, right? And there's an empty orbital when it comes to the carbocation. Okay? So just remember that. Okay? One more time. Carbocation, it's trigonal planar because it's sp2 hybridized, and it has an empty p orbital, right? There's nothing here. Whereas in a carbanion, we do have 2 electrons filled, right, in an sp3 orbital, which is trigonal pyramidal. Okay? Trigonal pyramidal. So radicals actually appear in trigonal planar sp2 hybridized or the shallow trigonal pyramidal sp3 hybridized, right? So here we have the one radical here in the trigonal planar, okay? Or it can do the shallow pyramid, quickly inverting from here to here, okay? Quickly from here to here, right? Which kind of makes sense because that's kind of like in between these two, right, where the carbocation is an empty orbital completely, okay, and it's trigonal planar, and the carbanion is trigonal pyramidal. It has 2 electrons in its sp3 orbital, right, in the carbanion, okay, so that makes sense. So radicals are neutral. They have no formal charge. That's important, but they still are electron deficient. Right? It's an incomplete octet. Okay? Radicals follow the same stability trends as carbocations, as they are both electron deficient species, right? So methyls are less stable than primaries, primaries are less stable than secondaries, and then tertiaries are the most stable, just like tertiary carbocations. Bond strength is inversely proportional to carbocation radical stability. So the more stable the resulting radical, the weaker the bond, right? So if we have a methyl bond here, it's the least stable as far as bond dissociation energy goes, right? Primary, more than that, more stable than that. Secondary, more stable than that. And then the most uh, uh, stable, right? Radical, which is the tertiary, right? Has the weakest bond energy, right? Has the weakest bond energy. Practice conceptual checkpoint 10.1 on Wiley Plus. So radicals like free carbocations are stabilized by resonance delocalization. Oh no, resonance again, right? But so in this case, right? In this case, that we're using fish hook arrows, right, or single barbed arrows to represent the possible resonance. So here we have an allylic radical, right? And the allylic radical can literally go through and do a single bond movement towards that, towards the center there, and then one of these bonds from this double bond, sorry, not one of these bonds, one of these electrons from this pi bond can move over, and then that makes it so that the other electron from the pi bond goes to the other carbon. Okay, so that's what you see here. And so now the net effect there is that the radical moves to the other carbon on the right side. Okay, it's the same for it's the same logic as doing resonance with double barbed arrows, right? Like normal arrows moving pairs of electrons, but this time we're just moving single electrons at a time. Okay? And then those arrows can come together to form a bond, right? Or they can go split apart to break a bond. Okay? The more resonance delocalized a radical is, the more stable it is, just like it is with normal lone pairs, right? So benzylic radicals, which is a benzene ring with an extra little methyl group on top of it. That's a benzyl, right? So benzylic radicals are more stable than allylic radicals because they have radical delocalization over more than one carbon atom, right? Over more carbon atoms, right? So here we go. We have those are not two single electrons, but we have one electron at the end of the benzyl on that methyl. Excuse me, on that methyl, and then one of the electrons from this pi bond right here moves to form a bond with that methyl's electron that's forming right there, right? And then the other electron from that pi bond moves to the top carbon, okay? And you can literally go around the entire benzene ring just doing that with the single barbed arrow. See, here we have two arrows coming together. Two single barbed arrows come together, meaning we're forming a bond right there. And then these are two single barbed arrows going apart from each other, which means we're going to break that pi bond. Okay? And we end up putting a radical there on that carbon. Okay? Do it again. Two single barbed arrows coming together to form a bond. And then two single barbed arrows going away from each other to break a bond. That pi bond right there. And now our radical is here. Okay, and then repeat the process again, and we end up with our radical back where we started. Okay, our radical back where we started. So resonance stabilized radicals are more stable than tertiary radicals, right? Which is actually the same trend that we had with carbocations. Remember, I was talking about before carbocations. Primaries are less stable than secondaries, which are less stable than tertiaries, and tertiary carbocations are the most stable carbocations unless you get a carbocation that is resonance stabilized, right? So same thing here, right? Tertiary to allylic to benzylic, right? Resonance stable radicals are more stable than tertiary radicals, right? Than tertiary radicals. Practical skill builder 10.1: drawing resonance structures of radicals on Wiley Plus. So vinylic radicals are especially unstable, right? Vinylic radicals are especially unstable. We talked about that before in the alkynes chapter, okay? And so that's the same also if you recall with vinyl cations, right? So we have vinylic first, right? And then primary and then allylic as far as stability goes. But again, going in that direction, we have decreasing bond dissociation energy as well, right? Decreasing bond dissociation energy. Okay? A radical in an sp2 orbital is less stable than one in an sp3 orbital, right? Right. And we've spoken about that. We've spoken about that also in the alkynes chapter, right? So practice this with Skill Builder 10.2, identifying the weakest carbon-hydrogen bonds in a compound on Wiley Plus. I know I'm going through this pretty fast, but literally the radical chemistry is very similar to the electron pair chemistry, right? So a lot of this should be reminding you, and should be review of the things that we've already talked about that are in the normal electron pair chemistry, right? Instead of radical chemistry. So, like ionic mechanisms, radicals also follow patterns, right? But radical mechanisms are distinctly different. This is where they start to diverge, and the reason why they start diverging is because of the the arrows that go far that go away from each other, meaning break a bond, and arrows coming towards each other with single barbs, meaning forming a bond. Excuse me. So here, this carbocation will rearrange to produce a more stable tertiary carbocation, right? But in this case, though, this radical will not rearrange to produce a more stable radical. Okay? Okay? That's another difference. That's another difference in these mechanisms, okay? A tertiary carbocation a carbocation will rearrange so that it can be more stable as a tertiary carbocation, but here this secondary one will not move. The molecule will not rearrange to make it a tertiary radical to make it more stable. And then the other difference is that the radical mechanisms follow 6 key arrow pushing patterns, which is what I was talking about. I only talked about a couple of them, which is the going apart to form a bond and going together to make a bond, right? But here are the 6 key arrow pushing patterns. The first one is the first one I talked about just a second ago, right? This is the homolytic cleavage, where we have 2 arrows going away from each other. That's homolytic cleavage that can be done by light or heat. We can also do an addition to a pi bond, right, where we have a radical halide, right, giving an electron, and then the pi bond from the one electron from the pi bond giving an electron, forming this new bond between the halide and the carbon, leaving you with a radical at the other carbon, right, on the other side. Okay, and then you can also do what we call hydrogen abstraction, right? And this is quite literally hydrogen abstraction. It is not proton deprotonation, and it's not hydride shifting or anything like that. This is literally hydrogen abstraction, because you are abstracting a hydrogen atom. That's neutral, by the way. It's neutral because there's one electron and one proton, right? So here we have a halide radical abstracting a proton, okay? Oh my god, I just messed up. Abstracting a hydrogen, okay? Leaving you with a alkyl radical, right? And a a halide. I don't know why it just blanked out on there. A protonated halide, right? Like a HBr or a HCl, right? I just blanked out on that. You can also do a halogen abstraction too, where you have a radical alkyl, right? And that radical alkyl will abstract a halogen from a molecular halogen, right? Giving you the alkyl halide. And when I say molecular halogen or molecular halide, dihalide, we're talking about things like bromine gas, chlorine gas, that kind of thing. And then you end up with a alkyl, sorry, not an alkyl, but a halide radical there. Number 5, you can do an elimination, which again is the reverse of an addition, right? Where before we were adding to a double bond, right? In step 2 or in number 2 here, right? Pattern number 2. Now we're doing the reverse, okay? Where we had the halide attached to the carbon as an alkyl halide radical, right? But now the bond between them will split. One electron going towards the halide, making the halide radical, and the other one going back towards making the double bond, making a pi bond to make a double bond with the free radical that was on the opposite carbon. So you get the double bond again. And then last but not least, we have the coupling reaction, right, where it is a reverse of the homolytic cleavage. And this is what I was talking about before, where two of them come together and make a bond, right? So now we have two radical halides, right? And their electrons will come together and form a single bond between, and that gives us a dihalide. Dihalide, right? A dihalide. Okay. So in fact, we could group all these 6 patterns into just 3 groups, right? Where we have the homolytic cleavage and the coupling, which is the one that's most common, the one I was talking to you about before we even got to the 6 patterns, right? Then the other one we can do is we can do the addition of a to a pi bond or an elimination, right? And then we have the hydrogen abstraction or the hydrogen abstraction, both directions, right? Both directions, okay? One is your abstracting a hydrogen from the alkyl group, the alkyl halide, right? And the other one is you're abstracting a hydrogen from the halide. Practical skill builder 10.3, drawing fishhook arrows. Okay, so the steps in a radical mechanism are classified as either initiation, termination, or propagation, right? Propagation actually goes in the middle. The initiation step, which is this one here, is a step where the radical species are formed from a non-radical species, right? So here we have a non-radical species, which is the dihalide, like a bromine gas or chlorine gas, Cl2, Br2, something like that. And they do homolytic cleavage, right? And so an electron goes from the bond, goes to each of them, right? A single electron goes to each of them, and you get 2 radical halides, okay? 2 radical halides. And again, I said propagation's in the middle, right? So propagation occurs when a radical reacts with a non-radical species to form a new radical in a non-radical species, right? So here are some of the patterns that we saw a few seconds ago, right? We have the addition to a pi bond, right? So this radical here will be introduced to this alkene, forming a new radical that wasn't there before, right? Same thing here. We have an alkyl halide. This radical halide will introduce its radical into the system, breaking that apart, making an alkyl radical and I keep on forgetting what I call these now. A halide, right? A hydrogen chloride or hydrogen bromide, right? So the point is, in all of these, right, we're introducing a radical after initiation. We're introducing a radical to a non-radical species, right? And then we get a new radical species, right? Same here, okay? Same here. We had a radical species right there, right? And now we get a new radical species, okay? That's propagation. And the last step of all radical reactions is called termination. And terminations happen when 2 radicals come together, right? And you form a non-radical species, right? And you form a non-radical species. So the complete definition of like a radical reaction is literally going from initiation, propagation to termination. This is called coupling, by the way. I think I said that before. So let's talk about the chlorination of methane, for example, right? Chlorination of methane follows a radical mechanism. This radical mechanism consists of 3 distinct stages, right? So here we have methane, and then we have light and chlorine gas, okay? And then we have methyl chloride and hydrogen chloride. How do we get there, okay? First, we do an initiation. Chlorine radicals are created with light, right? Like UV light or something, okay? Creates 2 chlorine radicals. Next, is propagation, right? And so one of the chlorine radicals comes over, right, and introduces itself to the methane, abstracting a hydrogen, leaving you with a, that should be not 2 electrons on there, but a hydrogen around there, because it's still a methyl group, thing, right? Leaving you with a carbon radical right here, right? Right here, carbon radical. Let me make that H there too. There we go. And a hydrogen chloride. So then the carbon radical can come over and do a halogen abstraction using a radical mechanism, leaving you with another chlorine radical, right? Oh, I'm sorry, I'm blocking that. Leaving you with another chlorine radical, right? And this keeps on going, right? All the way until you get two chlorine radicals coming together, coupling, thus destroying the radicals, making chlorine gas again. Okay? So that's termination. Okay? It occurs when radicals collide and couple, right? So we terminated there when we got this methyl chloride, right? And we terminated there when we actually made an ethyl group, right? So all those are possibilities where we have the two chlorine radicals come together, a methyl radical and a chlorine radical come together, or two methyl radicals coming together to make an ethane, right? To make an ethane. In each case, they coupled, and then the radicals are destroyed, and we terminate the radical reaction. Okay? Good stuff. So the sum of the propagation steps gives the net reaction, right? And here the net reaction is you get one methyl group plus a chlorine gas gives you methyl chloride and an HCl, which is what we saw as the reaction at the very beginning of this radical reaction. Okay, the propagation step is a chain reaction. The products for a later step serve as the reactants for the earlier step in the mechanism, right? Which is what we saw. So you can use this then, right? So sorry, let me say that again. Polychlorination then is difficult to prevent, right? And what that means is overchlorinating the methyl, like changing out all of the hydrogens through hydrogen abstraction and replacing them all with chlorines, right? And then you'll get this thing called carbon tetrachloride, right? Right. So methyl chloride is more reactive towards radical halogenation than methane, right? So you could get methyl chloride, right? And then you could happen again, and then you abstract another hydrogen and get methylene chloride, and then you can abstract it again and get chloroform, right? And then you can do it again with the last hydrogen, abstract another hydrogen, and you'll get carbon tetrachloride, which all these are actually used as organic solvents, by the way. Methylene chloride is used as an organic solvent. Chloroform is definitely used as an organic solvent. And then carbon tetrachloride is used as an organic solvent. If you remember, we used carbon tetrachloride back in the alkynes unit, right? It's one of those reactions, one of those reactants that we use in one of those reactions. So the need excess methane relative to chlorine for monochloration to be the major product. All right. So if you want to prevent polychlorination, right, or chlorination of multiple of the hydrogens that were on the methane, you have to have more methane than you do than the chlorine gas, which is kind of interesting because you're really chlorine gas and like methane are both gases and you're pumping them into each other, right? And you're like, well, how do I know how much is there, right? Well, you have to use like the pressure or the volume. So you can also have radical inhibitors, right? And what they do is they react with radicals and prevent a chain process from initiating or propagating, right? Stabilized radicals and compounds that easily form stabilized radicals are really good inhibitors. So, for example, oxygen is a diradical, right? Because it has one radical on one oxygen, one radical on the other oxygen, right? And it will react with two other radicals. And the hydroquinone will also react with two radicals. Radical reactions are very slow in the presence of oxygen. Just a fact to know. So hydroquinone undergoes hydrogen abstraction to form the resonance stabilized radical. So here we go. We have hydroquinone here, right? And we have an alkyl radical, okay? And it can literally undergo, right, hydrogen abstraction, as you see here, right? Hydrogen abstraction. Look at this. Well, actually, this single barbed arrow should come over here, like that, to give you the alkyl, right? The alkyl group with no radical and the resonance stabilized hydroquinone, which we've already done. This is literally just like doing a resonance stabilization with the benzyl group right there, where the double bonds form all the way around and come back again, right? Just like we saw before. That's resonance stabilized, okay? So you can actually do it again on the other side, another hydrogen abstraction, giving you an alkyl group that's been destroyed. Sorry, a destroyed alkyl radical. Now it's just an alkyl group, right? And then you get the benzoquinone, right, from the hydroquinone. Okay. Benzoquinone, right? Okay. So if we want to determine the process, if we want to determine whether the process is favored, we must then determine if the sign is negative or positive for delta G. Okay, and it turns out that in halogenation reactions, entropy is negligible. So all we need to really worry about is this part right here, right? Number of products equal the number of reactants equal the number of products, right? So here we have two molecules, some light, and then we have two molecules again, some light. Not some light, sorry. And so then what we're left with, and what we know then is that delta G is approximately delta H, right? And we say approximately delta H because we don't have the entropy term anymore, right? But the entropy term is negligible, and that's why we don't need to worry about it in halogenation reactions. And I'm not going to ask too much about that, so that's just a fact to know, especially when we're talking about this here. So you can actually estimate the value of delta H based on the bond dissociation energies for a broken bond versus the bonds made in the reaction, right? And we've done this before, right? We've done this before. We have broken bonds here where the bond between the carbon and the hydrogen is broken, right? And the bond between the dihalide is broken. And then we have bonds formed, right, after some light happens and we do some radical initiation. We have a bond formed between the carbon and the halide and then hydrogen in the halide, right? And so I want you to notice something here. There's chlorine and bromine right here, okay? Chlorine and bromine right here. And they are kind of similar right here, right, with these, their numbers as far as their bond formings and breakings, right? Right here. All these are the same because they're all breaking off that one proton right there. But you can see that these are kind of similar to each other, while the other ones are a little off, and you'll see why in a second. And let me just move my head real quick so you can see, right? These are pretty close together, but these are further apart from each other. These are pretty close together, and these are pretty close together, right? But the fluorine is way up here at 569, and then the iodine is way down there at 297. Same thing here, up here, or way up at 456 for the formation there of the methyl fluoride, and then the formation here of the methyl iodide way down there at 234. A little bout of dyscalculus there. 234, right? And we'll see some implications of that in just a second. I'll bring myself back now. Oops, went to the wrong one. Next. There we go. So now, just as you saw previously, I pointed out chlorine and bromine, right? Chlorine, or the chlorine gas and the bromine gas, right? And the effect of which is what you can see here from those bond dissociation energies. The fluorine, right, that had the huge number right here, right? 569 and 456 for those bond formations, right? Ends up having a delta H of negative 431. Holy mother, that's a lot of energy being produced during that reaction, right? That's incredibly violent. That's a violent reaction right there, okay? But on the other hand, over down here with the iodide, its delta H is down at positive 55. That's not going to happen, okay? That's not going to happen. Remember, we have spontaneous reactions like delta G when they're negative, right? And in here, and delta G is approximately delta H, right? In these cases right here, right? And so here we have negative 33 and negative 104. So those are doable, right? But positive 55, that's not happening. And then this one is just so high, it's so negative that it's not very practical because it's going to explode on you, right? That's not good. So, fluorination. Oh, this is literally what I just said in the previous slide, right? Fluorination is so exothermic that it's not practical. It's way too violent, right? With the negative 431. And then iodination is endothermic, not thermically favored, and does not occur, right? So really, only halogenation with chlorine and bromine are useful. Literally what I said in the previous slide. Okay. So interestingly enough, though, right, the first step of the propagation, right, here where we do the hydrogen abstraction, okay, it's actually going to be a positive delta H, and it's endothermic, right, for the bromine, okay, but it's still exothermic for the chlorine. But overall, though, in the net reaction, both are definitely exothermic. And that actually has implications on the reaction coordinate diagram, right? What it means is that the chlorination, since it's exothermic, right, it's going to have a much smaller activation energy, okay? And it's so exothermic that the reason why it's so exothermic is because the potential energy of the product is way down there, right? On the other hand, though, with the bromination, right, with the endothermic reaction, right, the endothermic reaction for the hydrogen abstraction means that you have a much higher activation energy barrier, right? And what that means then practically in chemistry is that bromination is much more selective. And what do I mean by much more selective? Okay. Well, let's talk about that. Okay. With substrates more complex than ethane, right? Multiple monohalogenation products are possible, right? Because you got two hydrogens here that you can get a hydrogen abstraction from, and then from the methyl groups you can get 6 hydrogen atoms abstracted, right? So 2 monohalogenation products are possible just from propane. Okay. Chlorine is actually indiscriminate. A significant amount of each product is formed. Right? You get this product here, and you get this product, right? You get this product and this product. Okay? Excuse me. And the reason why is, if you notice here, right, since secondary radicals are more stable than primary radicals, right, the secondary halide is definitely the more prominent one, right? It's 60% versus the 40% of the primary one, but they're still in pretty even, amounts, right? I mean, you're not far off from half and half there, right? Hydrogen abstraction from a secondary carbon is faster than that of a primary carbon, right? And you can see the reason why. And the reason why here is because my line there is really way off. But the activation energy, right? The activation energy to get to do the hydrogen abstraction from the secondary, right, is much lower than to get from the primary radical, right? Right, to get from the primary. But the point about this, though, is that you still get 60% of the primary, 60% of the secondary halide, and 40% of the the primary halide, right? So let me say that again. The point is, you still get 60% of the secondary halide, and you still get 40% of the primary halide, right? So that's not super selective. Compare that to bromine, though. If we were to do bromine, right, it happens much slower, right? And it's so much more selective than this. Since it is so much slower, it's so much more selective for the secondary carbon, right? And so you actually get 97% of the secondary halide here when you use bromine, and only about 3% of the primary halide. Okay, so the moral of this story here is that bromination is much more regioselective, right, than chlorination is. Okay, much more regioselective than chlorination. So if you want a halogen to be if you want a propane to be halogenated at the secondary carbon, right, at the secondary position, right, as a secondary halide, then you want to use bromine instead of chlorine. because here you get 97% of the secondary halide and only 3% of the primary halide. If you use chlorine, then you'll get almost the same amount of both. Okay. Oh, look at this, right? Oh, I lost something there. There we go. Look at this, right? If you brominate at the tertiary position, it actually happens 1,600 times more often than at the primary position, right? So even at the tertiary position, where we're talking about how tertiary radicals, right, were the most stable, right? Even when you use chlorine gas with the tertiary, you still get like 60. It's more than the secondary, but you get 65% of that and 35% of the primary, right? But when you use bromine with a tertiary, okay, it's approximately 100%, right, at the tertiary carbon, whereas we had 0% at the primary. So again, tertiary bromination. Bromination just in general is much more selective. You don't get mixtures of both. Okay? Whew. So the halogenation of butane or more complex alkanes, right, actually forms a nuclear center, which makes sense because we do have two hydrogens right here, right? And if we chlorinate one of them, right, there will be a hydrogen there and a chlorine there, right? And so we get a nuclear center. Turns out that 2-chlorobutane will form a racemic mixture, right? What does that mean? Recall that when you have a racemic mixture, you have a 50% mixture of a 50-50 mixture of the R and a 50-50 mixture of R and S, right? So there's 50% S2-chlorobutane and there's 50% R2-chlorobutane. Okay. Then also recall that the weakest carbon-hydrogen bond, the one with the lowest bond energy, right, bond dissociation energy, will undergo radical abstraction much faster than others, which makes sense. Okay, so alkenes will selectively undergo hydrogen abstraction at the allylic carbon, right, which is right here, right, the carbon that is allylic to the double bond, right, or the neighbor of the double bond, the carbon neighbor of the double bond, right. This is the allylic carbon right here, and it has the lowest bond dissociation energy. So hydrogen abstraction will happen there faster than at others. Okay, so let's do hydrogen abstraction, right, yielding the results of a resonance stabilized allylic radical, as you see there, right, going back and forth. You see that we have it moves the radical up there to that corner, right. So bromination of an alkene is selective for the allylic carbon. Okay, so we do a bromination with some light, right? Not chlorination, but bromination. Yeah, I guess you could do it with chlorination too, but we already found that bromination is way more selective, right? And since the hydrogen abstraction happens there the fastest, the bromine will go there. So we'll get brominated at that position the fastest. But addition of bromine gas to an alkene is a competing reaction. Okay. Whew, just a fact to note, right? So because of this, to avoid competing alkene additions, right? NBS can be used. NBS is this, the N-bromosuccinimide, succinimide, right? That's NBS. It can be used as a source of bromine radicals, right, instead of bromine gas. Okay, which is good because now you don't have, once you homolytically cleave bromine gas, you got two bromine radicals here, right? Whereas now, if you homolytically cleave bromine off of NBS, you just get one bromine radical, right? So using NBS keeps the concentration of HBr and Br low, so the competing addition reactions to the alkene are minimized, right? To the alkenes are minimized. So here we go. Propagation produces the allylic radical and the HBr, right? So we have our allylic radical happening there, right, with the hydrogen abstraction, and the bromine radical from the NBS, and now we have the allylic radical and the HBr. And then HBr produces, the HBr produced reacts with the NBS to form Br2, and then this Br2 then continues to propagate in the formation of the product, right? So now we have homolytic cleavage between the Br gas, and we get not another, but we get, I lost my train of thought. Oh, we got our brominated, our allylic halide. That's the word I was looking for, right? We get our allylic halide and our bromine radical, right? And that bromine radical can go and do another reaction. Okay? So with asymmetric alkenes, you actually get a mixture of isomeric products when you do the bromination with NBS. See? You get the bromine attaching there at the allylic carbon, and you also have a bromine there. The radical is delocalized onto two carbon atoms, so the halogenation occurs at either site. So there's this one here, and it can do resonance so that the radical goes over there, and so that's why you have bromination at both sites, right? At both sites. So practice with Skill Builder 10.7, predicting the products of alkyl bromination on Wiley Plus. Okay, so now we have ozone. Let's talk about some ozone, right, in the atmosphere. Turns out that ozone is both created and destroyed in the upper atmosphere, and there's no net reaction overall, but UV radiation is converted into heat. So heat is more disordered heat is a more disordered form of energy compared to light, and this process is spontaneous because the entropy is decreased, right? The entropy is decreased. Okay, so literally we have ozone in the atmosphere, right? And UV light comes in and turns the ozone into oxygen, right? And then the oxygen can be then recycled back into becoming ozone, right? Using heat. I mean, sorry, not using heat, losing heat, right? Losing heat to the atmosphere, okay? So this is the reason why having ozone, I'm sorry, my head is blocking the part of the product here. This is why having ozone in the atmosphere is important, because the ozone can block UV radiation from coming down to the surface of the Earth, giving you more skin cancer than it already does, right? The problem arises, though, when we have depletion of ozone, right? We have depletion of ozone, and the culprit is believed to be CFCs, chlorofluorocarbons. Okay, we've got CFC 11 here, which is Freon, and Freon 11, CFC 12, which is Freon 12, and CFC 113 or Freon 113. So my dad actually is like a general contractor, and he builds houses for a living, and all this other stuff that deals with construction, and he uses Freon a lot. Why? Because he uses it to fill up the compressors of air conditioners. I think that's what he uses it for. I could be wrong about that because I'm not an HVAC person, right? But he definitely, he has a lot of Freon lying around that he uses. Okay, and it turns out though that Freon that my dad's using is destroying the atmosphere. Right? It's letting all the UV light come through and give me skin cancer, right? Dang, Dad. Dang. Okay? They reached up, when it's released, these CFCs, when they're released, they reach the upper atmosphere and react with UV light to form chlorine radicals. That's not good, right? That's not good. And so here we have a CFC going up to the atmosphere, getting involved with, or not getting involved with, but getting involved with UV light, and it initiation starts, right? And you have now free chlorine radicals just floating around in the atmosphere, right? Why is this bad? This is bad because these chlorine radicals, right? Chlorine radicals will go and will go destroy ozone, right? Making these chloro-oxygen species, right? And oxygen, right? And that actually depletes the amount of ozone in the atmosphere. And so, since there's not as much ozone in the atmosphere, the UV light's not being absorbed as much, right? And then the UV light's not being absorbed as much, right? And so it's coming down here to the Earth, and it's giving you skin cancer when you're laying out in the pool, right? Yeah, it's crazy. It's absolutely crazy. So CFCs are bad. Chlorine radicals are formed during propagation and continue the destruction of ozone molecules. Right. The reason why ozone is better at absorbing the UV than the chlorine radicals are, the CFCs are, right, is because uh, once the CFCs do the homolytic cleavage and then they chlorinate one of the oxygens, they don't become CFCs again, right? To be able to absorb more UV light, right? But ozone, though, once it becomes an oxygen, once like a molecular oxygen, O2, right? Because ozone's O3. Once O3 absorbs UV light and becomes O2, it can then be recycled back into O3 and be used again, right? And so that's the big problem here. So industry has tried to find a way to rectify the situation, and they've done that by using HFAs, which are hydrofluoroalkanes. Okay. So interesting thing about hydrofluoroalkanes is that so I have asthma. At least I did when I was a kid. I probably still have a little asthma now. Not as bad as when I was a kid, but I used to take this inhaler called Ventolin, right? Or maybe it was ProAir, or maybe it was even Proventil. One of those three, right? It was all albuterol based. Okay. And I remember using my inhaler, and I would spray it, and I would breathe in, and it would work great. And I could feel it really working, really filling in my lungs, and I could breathe again if I was having, an asthma attack, right? But recently, though, like in the last 10 years, they switched all of the inhalers to using HFAs instead of CFCs because the old ones had CFCs in them, right? And you know this because there'd be on my inhaler, right? It would say, actually, I might even be able to have it. Hold on one second. Hold that thought. Put a pin in that. So yes, I was right, of course, right? So back in the day, so this is actually a recent inhaler I have, but so back in the day, inhalers for asthmatics, which were albuterol based, right, which is the active ingredient, they were being propelled using CFCs, right, and of course that's depleting the atmosphere. But I knew that when I was using, or I felt at least when I was using a one of those old inhalers that was being propelled by CFCs, right, I could feel the albuterol just filling my lungs and clearing it out, and I could breathe again during an asthma attack, right? But then they switched to, because of this, they switched to using HFAs inhalers instead, right? And so you knew that they switched to it because if you look right here, and I'll maximize the screen here so you can see, right? Focus, focus, focus. There we go, see? HFA, right? That says ProAir HFA. Okay. When they switched to HFAs, right, which is the hydrofluoroalkanes, right, and I would use this inhaler and try to breathe in, it wasn't as efficient. Like I felt like I had to puff like 3 or 4 times of it before I got enough, right? And so it turns out that like practically CFCs are a much better propellant, much better than HFAs are. Right? But HFAs are better for the environment. And so that's why they switch all of these asthmatic inhalers, right? These albuterol inhalers to HFAs, right? So that's a real that's the real practical thing here about organic chemistry, right? Here, let me show you one more time so you know I'm not joking or not lying to you, right? You see that? There it goes. ProAir HFA. Yep. Albuterol sulfate. Crazy stuff. Crazy stuff. Okay. So, sometimes called hydrofluoro. So there's also HFCs, which are hydrofluorocarbons, right? But they are not as harmful as CFCs because they don't have the chlorine radicals, but they still act as greenhouse gases. Okay. Right, they're sometimes called hydrofluorocarbons, but most commonly we see them as HFAs, like I showed you on my inhaler right there. All right, to auto-oxidation. Ooh, we don't like auto-oxidation. That's what makes your oil go rancid, right? Like when you've been using like your air fryer, not your air fryer, Back before we had air fryers, we had deep fryers. And if you were using your deep fryer for a little bit too long, the oil would get rancid. And how did it get rancid? It got rancid because of auto-oxidation. Okay? So auto-oxidation is a process by which organic compounds react with atmospheric oxygen to form hydroperoxide, right? So here we have cumin with some atmospheric oxygen, molecular oxygen, and then you get cumin hydroperoxide, right? This process is generally very slow. That's why it takes so long for your oil to actually get rancid. Okay? But this isn't oil. I'm just saying that's what I'm talking about with oil. Okay? So, of course, every chemical process has its steps, right? We start with an alkyl right here, right? Some kind of hydrogen abstraction from a hydrogen abstraction from some alkyl group, right? R group with the initiator, right? And you get the alkyl radical. Okay. Propagation occurs when the alkyl radical forms a bond, right, between itself and an oxygen, a molecular oxygen, right? And then another alkyl comes over, does another abstraction, right, of the of the hydrogen, okay, giving you the hydroperoxide, the alkyl hydroperoxide, right, and another radical, okay, another alkyl radical, and the termination occurs when the two alkyl radicals come together to form a new carbon-carbon bond, right? The initiation step here is actually a propagation step based on earlier definitions. So the definitions need to be revised. Scandalous. Okay. So propagation steps here can be more precisely defined as the steps that add together to give the net equation, right? And here the net equation is we have an alkyl group, right? Some molecule plus some oxygen giving us the hydroperoxide. So the initiation and the termination steps are those that are not part of the net chemical equation, right? Because these all get canceled out. Okay? So all you're left with is our oxygen and our alkyl and our hydroperoxide. So ethers are particularly susceptible to auto-oxidation, right? So here we have diethyl ether. With some oxygen, it can become a hydroperoxide, right? A hydroperoxide. Not to be confused with hydrogen peroxide, but a hydroperoxide. So hydroperoxides can be very explosive. So ether supplies cannot be stored for a long period of time, right? To say nothing of the fact that ether is super flammable too, right? But it's crazy though because I watch a show called MASH. I love the show MASH. It's so good. There was this one point when I can't remember what happened. All their gas tanks or something. Yeah, I think it was all their gas tanks were damaged or their power was out or something, and so they couldn't use their normal form of anesthesia, right? So they had these cloth masks over people's mouths, and they were just pouring very slowly some ether vapors over the mask and to knock people out, right? Yeah, dangerous stuff. So storing compounds in the dark containers prevents the light from accelerating the auto-oxidation process because light can't accelerate that process. Okay. Oh my God! Look at that. I was just talking about this, right? So triglycerides are important to a healthy diet, of course, right? We all love our fatty foods. But they're also susceptible to auto-oxidation. Allylic carbons are especially reactive, right? Especially reactive, okay? So here we have an allylic carbon on a trans fat. Oh my God, those trans fats are terrible, right? And it just got auto-oxidized. And so this auto-oxidation causes the food to become rancid and even toxic. Yeah, that's my head blocking that. It's just toxic. So don't use rancid oil, okay? Don't use rancid oil. I made that mistake a couple times. Luckily, I didn't die, right? But don't use it. Don't do it. It's bad for you, okay? Bring myself back here. Okay, here we go. So foods with unsaturated fatty acids have short shelf lives unless they're used preservatives are used, right? So one of the preservatives used is BHT, butylated hydroxytoluene, or BHA, butylated hydroxyanisole. And these preservatives they are radical inhibitors, right? They'll prevent the formation of radicals in the process of autooxidation, right? So one of the molecules, BHT, I already forgot what it stood for. Let's go back. There it is, butylated hydroxytoluene, right? One of the molecules, butylated hydroxytoluene, can prevent thousands of autooxidation reactions, right? BTH can go hydrogen abstraction and scavenge a radical that would otherwise initiate an autooxidation reaction chain, right? And so inhibitors like BTH are also called antioxidants. Oh my God. How many times have you seen health nuts? I'm sorry if you're a health nut. But nutritionists or whatever, or people say, "Oh my gosh, I need to get more antioxidants in my diet, right? I need more antioxidants in my diet." Well, this is what they're talking about. Okay, that's what they're talking about. These are antioxidants like BHT, right? Butyl. I'll remember this someday. Butyl hydroxytoluene. Is that right? Butylated hydroxytoluene. I was close. By the end of this lecture, I'll remember what BTH stands for. Coming back to you. There we go. Okay. So natural antioxidants prevent the oxidation of cell membranes and other biologically important compounds. For example, vitamin E. And you notice here, vitamin E has a super long carbon chain here, right? And so what it can do is that it can actually insert itself into like the cell membrane, because remember your cell membrane, if you've already taken biology class, or remember it from high school, your cell membrane is made of a phospholipid bilayer, and the lipid is a long carbon chain, right? And so this little long carbon chain here, and I don't know why I crossed it all out for you because you can't see it now. Let's erase it, right? Well, this long carbon chain here, right? Oh man, like, and it just slides itself right between into your cell membranes. And it's not a bad thing either, because vitamin E is an antioxidant, so it prevents your cell membranes from getting oxidized. That's a good thing, okay? And then my dog just woke up. I apologize there. He's just so excited about antioxidants like I am. Okay. So excited, aren't you, Kovu? Excited about antioxidants, aren't you? Okay, now he's looking at me like I'm an idiot. He does that a lot, actually. Anyway, another very commonly known antioxidant, right, is, right here. There we go, vitamin C, right? Vitamin C, also an antioxidant, right? And this is much more polar, so it gets dissolved in your bloodstream, right? In your in anything that's aqueous, right? So your blood, like your blood plasma, is aqueous, right? And so vitamin C, I think, is also known as ascorbic acid, right? I'm pretty sure vitamin C prevents scurvy, right? And that's why, like, the story goes is that. Let me bring myself back. You know that's vitamin C already. You don't need to remember the structure or anything, right? But the story goes is that back in the day, when there was a lot of ship-faring people, like pirates and sailors and stuff like that, on wooden ships, like clipper ships, they would require the sailors to eat a lot of lemons or drink a lot of lemon juice because it's full of vitamin C, right? And so the lemon juice, vitamin C, ascorbic acid, I believe, would prevent scurvy, right? And I've never seen a person with scurvy, but I hear, or at least I think I hear, that scurvy is an affliction in which your gums start to bleed, like from your teeth. Now who wants that? That's just, dang. As if back then, during those times, their teeth weren't already worse off already, right? Then you got your gums bleeding because you don't have enough vitamin C. Make sure you eat those oranges and drink those lime juices or lemon juices and stuff like that, okay? That's my tip for today. So, if you recall, oh man, wow, we're already at radical addition of HBr, right? we remember remember additions of HBr back in the alkynes and the alkenes, right? So we learned about that in chapter 9, where HX, right, or HBr will add across double bonds with anti-Markov-Rakov regional selectivity when peroxides are present, right? And this is just a review. Okay, we have Markov-Rakov addition here. Okay, Markov-Rakov addition here, and here the halide, the bromine, in a Markov-Rakov addition is adding itself to the side that has the most substitution, but then in an anti-Markov-Rakov, right, and that's in the presence of peroxides, it actually adds itself over on the side that has the least amount of substitution, right? There's more protons, or not protons, but hydrogens there. 95% of the time it will be that product when there's peroxides present. So the peroxides initiate a radical mechanism of addition, right? Different from the mechanism, different mechanism, different selectivity, right? And that's why anti-Markovnikov is this way. So here we go. Let's see what's happening here, okay? The reaction is initiated by a thermolysis, homolysis of the peroxide, right? So heat, which initiates the formation of the Br radical, the bromine radical, right? So the peroxide breaks apart, right, homolytically, and we have two alkoxide radicals right here, and or alkoxy radicals, they're calling it, instead of alkoxide radicals, alkoxy radicals. And then one of the alkoxy radicals will come over and abstract a hydrogen from the bromine, giving you the bromine radical, right? It's going to give you the bromine radical. Bromine radical comes over, and remember that the tertiary radical is more favored, more stabled. The tertiary radical is more stable and more favored, right? And it's a lot more than it is the secondary radical, right? That's why the secondary radical is not formed. And so the bromine radical will add itself to the tertiary radical, right? Leaving you then with a secondary radical here, right? On the it's not secondary radical; it's a tertiary radical over there, right? So. Let me just read this stuff for you, just so I can say I did. The bromine radical then, in theory, could add on either side of the alkene, but it will add to the side that generates the more stable carbon radical, right? That is the side with the lower energy intermediate. Thus is the lower energy transition state, right? And so, if it were to add on this side, right, on this side over here, you'd get this secondary radical, which is not as stable as a tertiary radical. And that's why it adds over here. Okay. So then the bromine radical adds to the less substituted side of the carbon of the alkene, generating the more stable, the more substituted carbon radical, right? And so we get that, which was the last slide, right? And then that radical, that tertiary radical, comes over, abstracts a hydrogen from another hydrogen bromide, leaving you with the anti-Markovnikov addition, right? Where the bromine is at the less substituted side and the hydrogen is at the more substituted side. The carbon radical can then abstract hydrogen to form a product and propagate a radical chain. Or two bromine radicals can come together and terminate the chain, or terminate the reaction. Or, exactly what I just said, or two bromine radicals can come together, right? Terminate coupling, right? Destroys the bromine radicals, and it stops the radical mechanism. Okay. So recall that addition reactions often form a new chiral center, right? A new chiral center. And so here again we have our alkene H bar with a peroxide going through a radical mechanism, and we get our anti-Markovnikov addition. If the substrate is not chiral, then a racemic mixture will be obtained, right, when a new chiral center is formed. If the starting alkene contains a stereocenter, then the mixture of diastereomers is formed, right? So practice that with skill builder 10.8, predicting the products. Polymerization now. So you guys know all about polymerization because your DNA polymerizes when it does replication, and then your amino acids polymerize when it becomes your secondary, tertiary, and then quaternary structures that are your functional proteins and enzymes. All right. So polymerization is pretty common in life. It's also pretty common in industry too, because we've talked about this before with plastics. Okay. So free radical conditions are also frequently used to form polymers. Recall that polymerization process joins together many small units called monomers in a long chain. So here we have ethylene, which is the monomer, right? And through free radical conditions, right, we can do polymerization and get polyethylene, PE, right, which is that plastic. that I showed you the other day, at the bottom of the plastic Tupperware container, right? At the bottom of the plastic Tupperware container. And that's our polymer, okay? So this is how it goes. This is how it goes. We start off with the peroxide, of course. Heat will cleave it homolytically, giving you 2 alkyl peroxides. We'll give you 2 alkoxy radicals. Those alkoxy radicals, one of them will come over, right? And then an electron from that alkoxy radical will join with 1 electron from a pi bond, right? Giving you the carbon radical, right? Giving you the carbon radical, right? And so that's the addition part, okay? Then that, sorry, my dogs are waking up. Then that carbon radical will continue the propagation, right? By having that radical from that original carbon, right? From that carbon there, come and join up with another electron from another double bond, right? From another pi bond, right? Leaving you with another carbon radical. So now you have another carbon radical. And this process just keeps on going over and over and over again. Before you know it, you get a really, really, really long chain of this carbon chain, right? The summation of the propagation steps gives the overall net reaction, okay? This is literally polymerization, right? Because you're starting with 1 carbon here, or actually 2 carbons here, and then you keep on adding more carbons from alkenes over and over and over again through radical combination, right? And it all started with the peroxide that got homolytically cleaved, giving you the alkoxy radical, okay? And once again, the this whole propagation thing can end when the alkoxy radical comes over, right, instead of an alkene, right, and it destroys the 2 radicals when the 2 radicals from the carbon chain and the alkoxy radical join together, forming a new bond. Both of the radicals are destroyed, and you've terminated the propagation using coupling. Okay, so it could happen either with the alkoxy radical terminating that chain, or it could also happen with the two radicals from two. It could also come from 2 carbon chains that have radicals at the end of them, right? And then you've just joined together the carbon chain, making an even longer polymer. Crazy stuff. Crazy stuff. Whew. So branching is also inevitable in this process, and it occurs by the following mechanism. Excuse me. Excuse me again. There we go. Ooh, that is really small. I can't even see that. Can you see that? Well, what's happening here is that the electrons in the bond between the hydrogen and the carbon, one of them is coming down to form this carbon radical, right? And then this one over here is going over here to be abstracted. The hydrogen is being abstracted by the carbon chain over here. So when that happens, now you have a radical in the center of the chain, right? And now that radical can go over and do a radical combination, right? Reform addition with an alkene there. And now you've made a branch chain with a radical at the end of what used to be an alkene. And then that can continue, just like the other chain can, right? And you can actually have this going on both sides, right? It could go from up here, just keep on going up here and keep on going here, like simultaneously. Okay? Good stuff. So highly branched polyethylene forms a very flexible plastic, like squeeze bottles or Tupperware, right? Unbranched polyethylene is brittle and rigid, like a plastic bottle cap. Interesting stuff. Interesting stuff. So here are just a couple examples of polymerizing things, right? Different carbon chains to make different plastics. We have polypropylene here, right? This is the propylene monomer right there, right? And then we can make polypropylene, and polypropylene's in everything. And so the reason why polypropylene is because, I don't know if you remember this, but a few days ago, right, I showed you the polyethylene plastic tub, and it was completely clear. You could see straight through it, the one that said PE in it, right? But then I showed you a Tupperware container that was black at the top bottom and then kind of cloudy, like not complete, kind of opaque, but still clear, kind of translucent top, right? That was polypropylene. So polypropylene is notoriously known for being cloudier, right? A little bit more opaque than polyethylene. But so the interesting thing about it though is that polypropylene is actually like dishwasher safe, and you can put it into things like heating things that go up to 121 degrees Celsius because its melting point is beyond 121 degrees Celsius. So you can do that with polypropylene, right? You can't do that with polyethylene though, right? You cannot do that with polyethylene, and polyethylene will just melt. Okay, and so if you ever use an autoclave and you want to autoclave like plastics, like for example microcentrifuge tubes, Eppendorf tubes, pipette tips, those are all polypropylene because they can withstand the 121 degrees of temperature inside of an autoclave to sterilize it. You can't put anything else in there that's like polyethylene, right, or polycarbonate because those things will melt. Okay, so that's also generally true with microwaves as well. Tupperware that's made of polypropylene can go into the microwave, okay, but Tupperware that's made of any other plastic, right, like polyethylene, right, will melt inside of a microwave. Okay. Other things to note too. Have you ever tried to use acetone? I know this is really old because I'm old. I'm actually not that old, but have you ever gotten like so stores will put like price tags on their plastic container like of things, right? Like for example, CDs or Blu-rays or DVDs or whatever, and they'll put their price tag labels on them that are sticky, right? Well, nobody wants that on their stuff, right? After they bought it. One of the things I have a lot of is like Funko Pops. They're like bobbleheads of different things, and sometimes they'll come in these plastic protective boxes. But the thing about it is that the price tag will be stuck on the box, and the box is made of polyethylene. So you peel it off and you get all this like sticky residue on it. And so you try to get rid of the sticky residue, and sometimes you use acetone. Bad idea. Because acetone interacts with polyethylene, making it all etched and cloudy and scratched up and looks nasty, right? But they use polyethylene because it's clear and you can see straight through it and you still see the pop. But if you were to have a polypropylene one, right, and you use acetone, nothing happens because the polypropylene is actually way more resistant to etching by acetone, right? So there's like a lot of these like real practical implications of the type of plastic you're using, right? And you've heard them all before. There's polypropylene, there's polyethylene, there's polystyrene, which is styrofoam, there's polycarbonate, which is really hard plastic. I think this is actually polycarbonate right here, like the top of the lid of a one of those metal tumblers, like those Ozark metal tumblers, right? Those are polycarbonate, I think. So yeah, polycarbonate is super hard and brittle, but it's also very clear as well. The most durable plastic of them all, though, is polypropylene. So a lot of Tupperware is made of polypropylene. All of the disposable molecular biology stuff is polypropylene. Yeah. So then we have polystyrene, of course. Styrene is the monomer. Polystyrene, then that's like styrofoam is the most common one. You've seen styrofoam before. That's all polystyrene. By the way, polystyrene also is incompatible with acetone. You try to clean anything that's made, you try to even touch acetone to polystyrene, and it just melts the styrofoam if you've never done that before. Then we have vinyl chloride. That becomes polyvinyl chloride or PVC. So that's the pipes, that we use in plumbing. Shower curtains, those gloves I was talking about before that you use for hand washing, all that stuff is PVC. And then we have one of the most favorites of them all is tetrafluoroethylene, which is actually Teflon, right? And Teflon literally is the stuff that the coating that they put on cooking implements, like pans and frying pans and pots and all that kind of stuff, so that it's nonstick, because not a lot of things stick to Teflon, right? And then you can just literally peel off like burnt cheese, from the frying pan. Or you can have like a fried egg and no butter, and then you just swirl it around, right? Because that's what they do on those cooking infomercials. Okay. Oop, went too far. So there are a couple of radical petroleum processes that you might need to be aware of. Not so much, but kind of, sort of, right? There's cracking, right? Cracking of hydrocarbons produces smaller alkanes and alkenes. So here we have a hydrocarbon, and it's being cracked into an alkane and alkene. We have an alkane radical here, right? There's also hydrocracking. It's done in the presence of hydrogen gas, and when you do that, all you get is alkanes, right? And then reforming is also a process too, producing branched alkanes. So heat, with an alkane, you'll get a branched alkane, right? So you've heard of cracking before from oil industry, hydrocracking from the oil industry. All right. Ooh, man, we've already gone through 67 slides. This is a long one, right? But I've only been recording for an hour and 20 minutes, so that's good. Usually something like 70 slides takes like 2 hours to do for me. So synthetic utility of halogenation, right? Bromine versus bromine. So chlorination to synthesize alkyl chlorides, right, is only useful when there is only one possible product, right? So here we have one possible product, right? Bromination is slower and more selective, however, like we were talking about before, and can be performed when several monohalogenation products are possible, right? And that's because, like I said before, bromination is super selective, right? Much more selective, right? And that was based all on the energetics, if you recall. I was just going to show you the rest of this molecule right here. There we go. So overall, the real advantage of halogenation is functionalizing an otherwise unreactive alkane, which can be converted into other useful functional groups, right? So here we have this 1-methyl hexane, right? 1-methylhexane. And you can use NBS to add a bromine to it, right? Use NBS on light to add a bromine to it via radical mechanism. Okay, and then you can take that to doing substitution or an elimination reaction to get more useful things like an alkane that is reactive. An alkene that is reactive, because the alkene, the double bond of the alkene, that pi bond can act as a nucleophile. Or you can do a substitution and add something else to it, a different alkane. Add a different halide. Right? So you have multiple possibilities. Multiple possibilities. Let me show you that. There's nothing there. That's just signifying multiple possibilities, right, after you do a substitution or an elimination reaction. Okay. Oop, went the wrong way. So this is just a quick review of the radical reactions that are synthetically useful, right, and will be applied to multi-step synthesis throughout our course. Not so much this course, because this course is almost over, but you'll see it a lot next semester, especially you're going to take me in the fall for Organic 2, right? We can do anti-Markovnikov addition, right, of HBr to alkenes, right, using a radical mechanism. We can use also we can also do allylic bromination using NBS, right? And then we can also do bromination of alkanes using bromine gas and light, right? So that actually ends today's lecture, right? So this is the last lecture before next week. So there are a lot of things happening next week. So let me just share the full screen here. And so I just want to make sure everybody knows what's going on and what's due and what's happening, right? And I think this is everything, right? Correct me if I'm wrong. But we do have the radical reactions assignment, right? That will be due tomorrow, right before the exam. Quiz 10 will also be due tomorrow, right before the exam. Okay. But then tomorrow will also be the exam, right? And then by the end of the day tomorrow, you'll also have your alcohol, your dehydration of alcohol lab due by the end of the day, right? Because that lab is assigned today. So make sure you remember to finish that along with your exam 4, okay? And then this is just a reminder, our lecture final exam is 1 week from today, on July 1st, and then our lab final is also 1 week from today on July 1st. Neither of those can be dropped, so make sure you complete those, okay? Make sure you complete those. All right, that's it for today's lecture on radical reactions. Next week we'll do synthesis, and then on Monday, and then on Tuesday we'll do alcohols, and then that will be it for the entire semester. It's all over after that, right? But I will see you later today in pre-lab for the pre-lab lecture on the dehydration of alcohols. All right. Good luck on your exam tomorrow. Again, I'm here to answer questions all day on Thursday, all day today on Thursday, right? But I cannot answer any questions about the exam or because I can't tell if you're actually asking a question just for your own, sake, or because you're actually taking the exam while you're talking to me, right? So I can't answer any questions about the exam content while we're during the exam times, right? Which is 8 o'clock to the end of the day tomorrow. All right. Good luck on the exams, and I'll see you in pre-lab lecture. Bye.